Okay, so this topic is going to be about complex numbers. Now, first of all, everything you've dealt with so far are real numbers. The real number line basically is the number line that everybody knows and loves, goes from zero and goes up to infinity and minus infinity.
Hmm.
Contains every single number known to mankind. Well, redundantly, contains everything, every single real number known to mankind. What does real mean? Again, redundantly, a real number means a number that can be shown on the number line. Sounds like a weird definition, but think about it, right? Every number that, for example, if I say, can you show me where 0.0000125 is? That's a weird number, but you can. If you zoom in about there, you will probably find it somewhere here, won't you?
Yeah.
Right? So you can spot any, even the weirdest kind of numbers, you can spot them on this. Even square root of 2, you can spot it. You turn it to a decimal, find where it would be, roughly here, I think. That's what
Okay.
I mean. These numbers are real. Even if they look weird, they're still real numbers.
Okay.
What is a complex number then? The problem is that when we do a little bit of advanced math, we find out that this guy shows up very often in our analysis in like mathematics. Okay. And
Hmm.
the problem is you cannot square root negative numbers, can you?
Yeah.
It's not- Because a square root means what do you square to get this number? Square root of -1 would therefore imply what would you need to square to get -1? Nothing. That's
Yeah.
impossible. At
Hmm.
least not on the real number line. So we come up with our first imaginary number, which is I.
Okay. Yeah.
I is literally defined as the square root of -1. This is the definition of I, then this is where the whole new field of math begins. Okay.
Right.
So this is called not a complex number, but an imaginary number.
Hmm.
We're going to use imaginary numbers to create complex numbers. Okay. So this
Okay.
is a imaginary, I'm going to remove the S here because it's a single thing. Okay. So
Okay.
this is the OG imaginary number, I. Okay. Now,
Hmm.
why do I say OG? Because technically you also get -5 sometimes. What do you do then? Well, you realize that -5 is really just -1 times 5, right?
Right.
And there's a rule, if you don't remember, I'll tell you this rule that you can distribute a square root, etc.
Hmm.
Powers can be distributed across multiplications. So, why did I do this? Because I like to put the OG imaginary number whenever
Hmm.
possible. Okay, so we always like minus root of -5, we write it down as I times root of 5. So that
Right.
it's always the I that shows up as the imaginary number. Okay,
Got it.
so just wanted to show you this example. Now, uh, so now what is an imaginary number? So now let me show you an example of, how I said that when you do some advanced analysis, you keep like, coming face to face with a guy like this.
Hmm.
Let me show you a simple example for when. For example, when you try to solve this equation. Now, up until now, you've been told that this equation does not have any solutions because when you do this, you can't
Hmm.
square root it because there's no real answer to this, right?
Right.
However,
Hmm.
you can square root it now because you've opened up a new field of math for yourself where square root of -1 exists.
Okay.
So you get plus minus I as your answer. You get two imaginary numbers as your
Right.
answer, like plus I and minus I, what I mean by that.
Hmm.
And therefore, you find out that the rule that we've always said, quadratic equations always have two solutions, is in fact true. Because previously your teacher told you that this guy doesn't have any solutions. But what they should have said is they don't have any real solutions. They do have solutions. In fact, two of them. But
Hmm.
they're just not real. They are imaginary solutions. Okay. So these are all pieces of the puzzle that will come together in a bit. Now, sometimes we are asked to simplify complex numbers. For instance, if I tell you, can you write this down in its simplest form? The first
Okay.
thing you should do is take out that -1 out of
Hmm.
it. Now you have this. The
Hmm.
next thing you should do is realize that the root of -1 is just I, looks cleaner that way. And the root of 9 is what?
Is just the root of 9.
Which is
Or
3.
wait. Yeah.
Yeah. So we've simplified our complex number. Do you
Yeah.
remember simplification of surds?
No.
Okay. So that is an idea we're going to need for this chapter also, but
Okay.
we'll talk about it as we come to it.
Hmm.
So, for instance, let's say that I'm going to give you a little taste of it. So, simplify the following.
Mm-hmm.
The first one is root of minus 18. Okay.
Mm-hmm.
Now, whenever you see a minus in a square root, the first thing you should do without thinking is just take that minus 1 out. Okay, and
Okay.
then look at the number separately. So the minus 1 is just I. Now, here's what I do. I want to simplify this thing. We call this a surd, by the way. Okay.
Mm-hmm.
What is
Okay.
a surd? A surd is a thing with a radical on top. Radical means root, by the way,
Mm-hmm.
on top. That is not, that cannot be converted to a whole number.
Mm-hmm.
Okay. What do I mean? For example, root of 9, that is not a surd because it's even though it has a root on top of it, root of 9 is just 3. So we can
Mm-hmm.
convert it to a whole number. But root of 18 doesn't have such a situation. We can't directly convert root of 18 into a whole number.
Yeah.
So it has a radical on top, it has a root on top, but we can't convert it to a whole number. So it's very unsimplified. We like to simplify surds. How?
Mm-hmm.
Think about breaking 18 down into a square number times another number.
Right.
What is the biggest square number that I can break 18 down into?
9.
And what would I need to multiply 9 with to keep this consistent?
2.
Exactly. Now, why did I do that? Again, because of this rule.
Mm-hmm.
I can break down root of 9 times 2 into root of 9 and
Mm-hmm.
root of 2. And why did I do that? Because root of 9 is clean. It's a whole number. So I've
Okay.
made root of 18 into a much simpler looking surd
Okay.
because it's now just root 2. Okay? I'm sure a elementary school kid would probably find this to be worse than that. But we call this simpler because algebraically speaking, simplified means smaller numbers. Okay?
Okay.
So you see
Okay.
the root is a smaller number now, so that's all we care about.
Mm-hmm.
Again, the I is just kind of tagging along. Okay, the minus in the root turns into I. Once you do it enough times, you'll probably start skipping this step altogether. You'll just
Okay.
directly write the minus as I and put the positive number inside. Okay?
Mm-hmm. Got it.
Okay. Next up, we have the powers of I. What do I mean? See, I is root minus 1. That's its definition.
Mm-hmm.
However, think about what I square should be then. What do you think I square is?
-1.
Exactly. What do you think I cube is?
-1 squared.
Mm-mm. So
Minus 1.
I cube means I times I times I, right?
Right.
In other words, I square times I.
Mm-hmm.
And I square we know is minus 1.
Mm-hmm. So
And
-1.
I is exactly minus I basically. So I cube is just minus I.
Okay.
Okay. What is I to the power of 4 now? Basically, just think about multiplying the previous thing with another I. So think about multiplying this with another I. What would it become?
-1 times the root of -1.
No, no, no. No, minus I times the root of. No,
Yeah.
wait, what? So minus I
Mm-hmm.
times I, right?
Yeah.
Which is, what is I times I?
So it's -I squared.
And what is that?
Oh, 1?
1.
Yeah.
Oh, yeah?
Okay.
Okay, what is I5?
Okay, so that's 1 times uh I.
Which is just I.
Right.
You see? So I is I. So it starts with I
Mm-hmm.
and goes to minus 1, then goes to minus I, and then goes to 1, and then goes back to I. And
Okay.
then it keeps repeating like that because the sixth
Yeah.
power, so I'm gonna write this actually here, and then the sixth power is again minus 1, and then the seventh power is again minus I, and then the eighth power is again 1.
One.
So you see, it's a pattern. All you gotta do is understand the first four and then kind of just think about adding powers of 4. Sorry, multiples of 4. For
Got it.
example, if I is I, then I to the power 5 is also I because we're just adding 4 to the power.
Got it.
And if we add another 4, we will again end up at I. And
Okay.
same thing here. 2 plus 4 and 6 plus 4 will again give me minus 1. And you see? So every 4 later, you're going to get the same thing you're at right now. Okay?
Got it.
So this is an interesting little thing that you should also be familiar with. Not going to be very useful, by the way, in your exams because in your calculator you can do this anyway, but you should know the basics, the basic ones, okay? Like off the
Okay.
top of your head, you should know immediately that I square is -1 and I to the power 4 is 1.
Got it.
Okay. So far we've been talking about the imaginary number I. We haven't talked about anything else, right?
Mm-hmm.
But this chapter is called complex numbers. So what's that all about? Now let's introduce complex numbers. Complex numbers are numbers that are created by combining a real part and an imaginary part. Okay?
Okay.
So for example, 3 plus 2i. So you see, this is the real part.
Mm-hmm.
This is the imaginary part. Okay? So
Yeah.
we call the real part the RE part. Okay?
Mm-hmm.
And this is the imaginary part. Similarly, 4 minus, I don't know, 3i. Real, imaginary.
Right.
So this is imaginary, this is real. Again, this is imaginary, this is real. Okay?
Got it.
These are called complex numbers. Numbers that are like a combination of a real part and an imaginary part. In general, complex numbers are denoted by the letter Z. Okay? So a
Okay.
general complex number will look something like this. So we will say that this is the real part of the complex number,
Mm-hmm.
and IY is the
Imagine.
imaginary part. Okay?
Okay.
And this is the anatomy of a general complex number. Now, of course, if the real part is 0, then we say that it's a purely imaginary number. Okay?
Right.
Like for example, if it is 0 plus 2i, this is purely imaginary.
Mm-hmm.
And if the if the real part is, if the imaginary part is 0, we call this purely real or just real, if you want to save your breath. Okay. So there's a bit of a like a what's the word? Notation thing. If I say RE of, so curly braces, Z,
Mm-hmm.
what I mean is I'm asking you what is the real part of Z? You will say X.
Okay.
If I say I am curly braces of Z, I'm
Mm-hmm.
asking you what the imaginary part of Z is. This time you will say Y. You won't
Okay.
say YI, by the way, you'll just say Y. Okay? Because we're
Mm-hmm.
talking about the imaginary part's coefficient, basically. Think about it like that.
Yes.
Okay?
Okay.
So this is like almost a command. I don't know if you do development like programming, but it's a command. I'm saying the real part of Z, extract that and tell me what it is. Imaginary part of Z, extract that and tell me what it is.
Okay.
Uh, when are two complex numbers equal? If their real part and their imaginary part is exactly the same, they are considered equal complex numbers, which is very self-explanatory, I think, right?
Mm-hmm.
Okay. Um, so I'm just gonna write that down for completeness. Equal complex numbers are such that the real and imaginary parts are equal.
Okay.
Okay, that's what makes them equal. Now,
Mm-hmm.
what is a conjugate? This is an important thing.
Mm-hmm.
Conjugate of complex numbers. Every complex number in the world has a conjugate. Basically, its cousin. Okay?
Okay.
How does it work? For example, 2 plus 3i. He has a conjugate, which is 2 minus 3i.
Mm-hmm.
Basically, just the flipped imaginary part. Okay? So
Okay.
flipped. That's it. These two guys are conjugates of each other. For example, -2 minus 4i. What do you think the conjugate of this guy is?
-2 plus 4i.
Exactly. Now, a lot of people make this mistake where they flip the real number sign also. But don't
Okay.
do that. Conjugate only has the imaginary part flipped, okay?
Okay.
So very careful.
Got it.
And that is conjugation. Finally, let's talk about um, solving, for instance, a quadratic equation.
Mm-hmm.
So, for example, let's say that we have a quadratic equation that looks like this. 5z square plus 14z plus 13 and you want to find its answers. Okay. By the
Okay.
way, they're being annoying by putting z's here. Doesn't matter that there's a z there. So for example, x. So how do we solve this? The thing is, because I hope that you already understand that we're expecting non-real answers, right? We're expecting complex answers.
Yes.
The splitting the middle term method won't work here. That only works for real answers. So we need to use either completing the square or what's the guy? Quadratic formula.
Yes.
So let's use the quadratic formula just to see why we get complex answers anyway.
Okay.
Minus b plus minus b square. I think it's 169 or
Uh, yep.
what is 14 squared?
196.
196, okay.
Yes.
Minus 4 times a times c
Right.
divided by 2 times a, which gives me minus 14 plus minus, what is this gonna be?
Eight.
196 minus,
It just gives me 8i in the
yeah,
8.
it should.
Right.
It should, because it's going one step further, but let me show you why.
Yeah. Yeah.
So remember at some point you probably learned about quadratic formula that if the discriminant is less than 0, you're gonna not get any real answers.
Yes.
Right, this is why. Because when the discriminant is less than 0, you have a root of negative 64. If you just look at this for a second, you will realize, first of all, again, minus can just be taken out as an I,
Mm-hmm.
and this is just 8i, because
Yes.
the root of 64 is 8, which means we really just have this, minus 14 plus 8i over 10,
Mm-hmm.
and minus 14 minus 8i over 10. As you can see, these guys pop up in conjugates of each other always,
Mm-hmm.
just because of how quadratic formula works. So
Okay.
these are your two answers. They're clearly complex because you have a real part, well, a real part and an imaginary part. Okay.
Okay.
So the real part is minus 14 over 10 and the imaginary part is 8 over 10. Okay. And here the real part is minus 14 over 10 and imaginary part is of course negative 8 over 10 because it's a conjugate.
Okay.
Good. Now, um, thankfully, adding, subtracting, multiplication, dividing, everything about complex numbers is the same as basic algebra. Okay.
Okay.
So everything works the same way. Let me just show you what I mean. Maybe I can show you on the book. One sec.
Mm-hmm.
So as you can see right there, if you want to add these two complex numbers, just add their real parts together and add their imaginary parts together, which gives you plus 2i, because 3i minus I is going to be plus 2i. Okay.
Okay.
Subtraction, same thing.
Mm-hmm.
Multiplication, same thing. But during multiplication, you will often have a situation where, as you can see right there, when you multiply 2 with 8, you get 16.
Mm-hmm.
When you multiply 2 with negative I, you get minus 2i. When you
Yes.
multiply 3i with 8, you get plus 24i. Here's the fun part. When you multiply 3i with minus I, you get minus 3i squared.
Mm-hmm.
However, we know that I squared is just minus 1, which means that minus 3i squared is just plus 3,
Right.
right? So
Okay.
be on the lookout for these little powers of I, okay?
Got it.
Um, and okay, this is an important little idea also.
Mm.
Remember that if you ever multiply a complex number by his own conjugate, whenever
Okay.
you multiply a complex number by its own conjugate, you will always end up getting a real number answer. Why? Just because of how the basic math works. You
Mm-hmm.
see, when you have two conjugates, you have a plus b and a minus b, don't you?
Yes. So those
And
cancel.
like, yeah, because you have a is 2 and b is 3i. So a square is 2 square minus b square, which is 3i square. So you have 4 minus 9i square. But the thing is, I square is minus 1, which means
Yeah.
all of this is really just plus 9. So that is
Right.
why whenever you multiply a complex number by his own conjugate, you always end up getting a real number.
Okay.
Remember this because I'm about to show you why this is so useful for us.
Mm-hmm.
Okay?
Okay.
There's something called rationalizing a fraction. If in a fraction we end up with a complex number at the bottom or an imaginary number at the bottom, okay,
Mm-hmm.
we like to rationalize it. What is that? Rationalizing means removing the complex number from the bottom. We don't like imaginary stuff sitting downstairs, okay?
Okay.
So what we do is to convert this complex number into a real one, we multiply him with his own conjugate because we know that if we do that, the complex number is going to die out and convert itself into a real one. But we
Right.
can't do it just to the bottom, so we do it to the top too.
Mm-hmm.
So that's
Okay.
called rationalizing a fraction. Okay?
Got it.
So as you can see, we get this guy. We already know that it's going to be 2 squared minus 3i squared, which
Mm-hmm.
gives me 13. And at the top, I have a bit of a mess to deal with, but I don't care because my actual problem is averted. My denominator is no longer a complex number.
Okay.
Okay, so I don't mind that the top is a bit messy now. In fact, it actually becomes pretty clean, but
Yeah.
still, a very important little idea. You might get a question on this. The
Mm-hmm.
cool part is you don't need calculators for,
Yeah.
be working with basic complex numbers at least.
Okay.
Okay, so I think let's stop here for now. The next
Okay.
idea is pretty straightforward. Actually, it's very, very easy because now that you know the basics of complex numbers, all of this is going to be extremely easy. Might look complex, but you're going to find it to be super, super easy.
Okay.
Just do like a few problems out of this just to get some practice, but I think the ideas are not that tough.
Okay.
Um, Question 6, by the way, is a bit of an important one. Let me give you a hint on this because it'll be useful for you if you try out some of these. You see,
Okay.
if I tell you that a quadratic equation has these roots, x equals 5 and x equals 2, you can find out what the quadratic equation was by reverse engineering, basically.
Mm-hmm.
If x equals 5 is a root, then what must have been the factor?
Um, 25.
No, no, x minus 5. Because if you set
Oh,
this guy to be equal to 0, you'll get x equals 5, right? So I'm reverse engineering what it should have been before.
right. Okay.
And according to this, it should have been x minus 2. So the quadratic equation that this came from is this one. And I can
Mm.
open it up
Mm.
and
Okay.
this. So you see what I did there? Pretty
Yes.
simple, right? But you don't really think about it the other way around. So you're
Yeah.
going to do the same thing here. As you can see, we want a quadratic equation that has these roots. Do the exact same thing. X minus negative 7i,
Mm-hmm.
or you can say x plus 7i basically.
Mm-hmm.
Because to get x equals minus 7i, you're going to need x plus 7i. And
Mm-hmm.
to get 7i, you're going to do x minus 7i, right?
Okay.
As a general rule, just to kind of, make it a general thing, if I tell you that a quadratic equation has alpha and beta as its roots, the quadratic equation will always be x minus alpha, x minus beta. So
Okay.
whatever you have as the roots, just put them here and here in brackets so that the negative applies to everything in them. Okay.
Okay. Got it.
So of course I'm sending you the recording so you can like kind of refer to this when you're doing this question, but definitely
Mhm.
try question 6.
Okay.
Um, and give these not 10. 10 is just pointlessly complex, but 7, 6, 7, 8, and 9 are super important questions. Try these out. Okay.
Okay. Got it.
Another interesting thing I just want to tell you is look at question 9. It says that this is a root of an equation. Now, a normal person would be like, okay, I know one root. I need two roots to find the quadratic equation. Where's the other root? What do you think?
Right. The same? The conjugate?
Exactly.
Yeah.
Every single time quadratic equations give you conjugate roots. Okay. In
Okay.
fact, every equation in the world, even if it's cubic, quartic, whatever, whenever when you get one complex root, you're always gonna get his brother with him. They come in a package. Okay.
Right. Okay.
So that's basically the idea. And next class will basically wrap it up with the Argand diagram, and that's
Mm-hmm.
basically it.